Hello everyone, my name is Artyom, and today let's talk about system calls, or syscalls for short. Let's start with the hard truth first. User applications cannot do anything other than burning CPU cycles without asking kernel for help. Let's say opening files, establishing network connection, writing to the terminal, spawning new processes, everything needs to be facilitated by the kernel. So I figured it would be fun to actually take a closer look at what syscalls are, how they differ from regular function calls, what they look like in code. I guess it's gonna be fun and interesting and quite educational. But before we jump into coding, we need a bit of background information first. So check this out. Alright, so it all starts in the hardware. A long time ago, CPUs had just one mode of operation called real mode. In real mode, programs could do pretty much anything. And although that was quite a simple conceptual model, it had many drawbacks. That's why after a while we've got something called protected mode. Now, in protected mode, different programs had different access to resources based on their privilege level. Okay, in modern x86 CPUs, there are 4 different privilege levels, also called rings or rings of power, and a ring, like first ring, ring 0, has access to all hardware resources. It can execute any instructions, it can do anything. So this is where kernel usually lives. Now there is ring 1 and ring 2. These privilege levels are for drivers. And finally, there is ring 3. Okay. Ring 3 is also called user space or user land, and this is where regular user applications live. So applications in ring 3 cannot do much, as was told before. They can't access files, they can't access network, they can spawn new processes. And this actually makes sense, because just imagine if any application in your computer could access network, like network device, and therefore like sniff on the traffic, or could read other applications' memory. That would be a security disaster. So it's a good thing that ring 3 is so limited. But now we want our programs to do something meaningful, right? We want them to access files, to, talk to the network. Therefore, we need some way for ring 3 applications to ask kernel for help, since kernel can do pretty much anything, right? So but then there's another problem, okay? Applications at ring 3 cannot just voluntarily change their privilege level to ring 0, because that would again compromise the whole idea of privilege levels. So we need some mechanism to call into kernel, or call kernel functionality from user space, okay? And this mechanism needs to be secure, okay? Good. So this is what we call syscalls. A secure mechanism to call kernel functionality from user space. And one thing that we need to understand is that this whole thing, it doesn't happen just in software or just in hardware. It actually happens in collaboration between software and hardware. Good, so now that we have enough background information, let's jump into code and see what it looks like. Let's start with something simple. and nothing can be more simple than a program that does nothing, or more specifically, a program that starts and then it exits with a specified exit code. So let's create a new file and call it empty. Now, to really understand what's going on, we want to be as close to the metal as possible. So we will just use assembly to write the program. So let's use .s extension. And now let's flesh out the skeleton of the upcoming program. So we'll start with the text section. And now we need an entry point to the program, a start label. We're gonna take small steps and evaluate what we have after each step. Now we need to use global instruction to export this entry point so that when we actually try to turn this assembly file into an executable, the tooling can find this entry point. Now we need to turn this assembly file into an object file. And we're going to use as command for this, short for assembler. And we are going to build a 32-bit object file. I'll explain later why. So we're going to produce empty.o file, and then we need to turn this object file into an actual executable. And this is where we will use ld command, which is a linker. And we will ask this linker to build a static binary. And again, we need a 32-bit elf executable. So that's what we're gonna type here. All right, so now we have a binary. Let's try to run it. And something isn't quite right. It says format error. Maybe something is wrong with the assembly. So let's try to add some instruction here. Let's say return instruction and see whether it executes or not. So we need to do the assembling and linking again and try to run it again. And all right, so now we have a segmentation fault. So clearly something is happening and we clearly build like a proper executable. Now we can just call return here. Return will take whatever is at the top of the stack and try to use this return address. And our top of stack is pretty much garbage. To end the program properly, we need to call into the kernel. Basically, we need to invoke exit system call and provide an exit code for the system call. A little bit of searching on the web tells that to invoke system call, we need to issue an interrupt, but the source is the truth. So to spice things up, let's actually look it up in the kernel source code. So let's first try to download the source code. Okay, first link, this is Linus's mirror on GitHub. Let's clone it. Git clone. All right, this is gonna take a while. We are nearly done. Awesome. Let's open up the source code and open entry64compat.s. This assembly file has some documentation about 32-bit calling convention. And here we can actually see that the system call number should go into EX register and first argument goes into EBX register. Our exit code therefore goes into EBX, but we need a system call number for the exit system call. There is another file called syscall32tbl, and here we can see that exit syscall has number 1. Okay, so now we have enough to proceed with the coding. All right, system call number 1 goes into EX register. The exit code, let's say 42. Why not? 42 is a good number. This goes into EBX. All right, now we need to issue an interrupt, and this needs to be 80 in hex. All right, that's just a Linux convention. And that's pretty much it. So let's assemble. New lines. Okay, again. Good. So now we link. And let's run this binary. Okay, no error. Let's see the exit code. 42. All right, that's exactly what we need. But note that an interrupt is not a regular function call. It's not a simple jump. There is actually a lot of overhead involved in handling of an interrupt. So certainly people came up with something better and faster. And yeah, let's dive into the holy moly of systems programming. Let's open up AMD Architecture Programmer's Manual and search for something like fast system calls. Okay, we can see a special section. Let's go there and see that there are two instructions, syscall and sysret, that are a low latency way to invoke a system call. Awesome. That's what we're gonna use for the next section. But before we jump into coding, let's check something in the Linux source code. We need to open up entry64 assembly file and scroll down for the documentation on the calling convention. So here we see that system call number goes into arrayx register and argument 0 needs to go into RDI. So now we need to check the 64-bit syscall table and let's search for exit. Okay, so now it's not 1 but rather 60. Let's go back into the editor and all right, so we need to move 60 immediate into rex. Then we need to move the exit code, which is 42, into RDI according to the calling convention. And finally, we need to issue a syscall. That's a processor instruction. Then we need to assemble this file into an object file. And here we don't need any fancy flags since we're building a 64-bit object file on a 64-bit host. And the same comes to linking. We don't need this extra flag, we just remove, and by default it'll be 64-bit. So we have the new executable. Let's run it and let's check the exit code. All right, this is like magic. 42, this works. Awesome. But I guess this is time to try something a little bit more interesting. And let's create a new file for this, or rather copy an existing one. And let's rename it to hello. And now this exit sequence, we need to rename it. Let's use an exit label for this exit sequence, and start entry point, we'll just jump to exit, at least for now. Let's check that we didn't mess up anything. Let's assemble again. And now, as you can see, the file name is different, hello S to hello O. And now let's link again. And here we need to again say that we're building a static binary. And let's run it. Perfect. Okay, so far so good. Obviously, as dictated by law, we need to make this program output hello world into the terminal. Okay, so to do this, we need to invoke another system call called write. And we need to write into first file descriptor, which corresponds to standard out. I don't remember exactly the arguments to write, so let's look it up in the manual. Okay, so first argument is indeed a file descriptor, which is just a regular number. Then we need a pointer to the start of the string. And finally, we need the number of bytes to write. Looks like I forgot which argument goes into which register. But anyway, let's look it up in the source code. First, we need like a system call number for write. And as we can see, write is actually system call number 1. Okay, now what about the calling convention? Let's switch to entry 64. And here, okay, first argument RDI, second argument RSI, and then RDX. All right, let's continue. So we move 1, which is write system call number, into rax. Then we move file descriptor number 1 for SD out into RDI, and then we need to move start of the string into RSI, but we don't know it yet, so let's just put a question mark there. And same for the number of bytes to write into RDX. Okay, so let's define a string as part of the assembly. For this, we need to create another label. Let's call it hello message. And now we will use an assembler directive string to embed this hello world string into the resulting object file. Good. Now we have the string. Now let's fix up the assembly here. Let's replace this question mark with hello message. Awesome. And now we have the third argument to write, system call. And this is a number of bytes to write. Let's see, 1, 2, 3, 4, 5. Oh man. All right, so let's instead make assembly calculate this number of bytes to write, and we will use this little trick to do this. Now we go back and replace this with hello message len. Good. Let's try to assemble the program. Okay, looks like we need to fix something. Oh, whoa, we actually forgot to issue a syscall instruction. All right, so okay, that's fixed. And then, okay, arrow data is not a thing. Let's delete this. Okay, fine. So let's try again. New lines. Okay. Again. Good. Then let's link it and run the binary. Huh. Don't you seg fault on me. Okay, fine. Let's debug this. Let's use GDB, which obviously stands for greatest debugger, right? Step 1, breakpoint at start. Then let's switch layout to assembly. Okay, run. Now step. It's segfaulted, but it's segfaulted before syscall, actually at the move instruction. Let's see. Move instruction can take either an immediate value, a number, or a memory location to move from. But here looks like we are trying to move from F memory rather than move F immediate here because of the missing $sign. This is frustrating when your program segfaults because of not enough dollars. But all jokes aside, assembly is tricky and you need to just pay a lot of attention to what you're doing. All right, getting back to the code. Now let's fix this bug. We need to go back to the source code and then fix a couple places, add a little bit more dollars. Okay, closing GDB, then reassembling and relinking. Now let's run the binary. Hello world. Okay, so now we can actually invoke syscalls from the assembly. This is like the lowest level, extra raw. But although we can, should we? The answer to this is probably no. Instead, we better just use wrappers provided by libc. And so let's re-implement what we had, but now in C instead of assembly. So starting with this simple stub, C program stub. Now let's compile this. Yeah, so by default, this is in a.out. Let's actually recompile and use, let's say, hello C as an output and then run this binary. Okay, so far so good. Now let's actually check the manual on the syscall function, which is a wrapper in libc that takes care of all the low-level details it takes to actually invoke a syscall. So we need two headers here. All right. Syscall.h. Okay, good. Now let's create a string. So let's call the string message, and the message will be hello world. All right. Let's actually check this. Should be a pointer. Okay. Okay, fine. So the next step is to call a syscall function. And here we can actually use the constant from the header instead of just writing 1 for the syscall number. And the second argument needs to be a file descriptor, which is 1 in our case. Then we need to use message as the third argument. And yeah, let's add a new line here. And then the final argument needs to be the length of the string that we want to write into stdout. Let's check the manual again for the strlen function. Okay, so we need to include string h header, and then it takes just a regular pointer. Okay, fine. Now let's fill those in. Good. Save. Then compile. And it works. Obviously, these are just some toy examples, but they are enough to understand what is going on under the hood. We did miss some details, like when we invoke system calls with an interrupt, the interrupt vector needs to be set up beforehand by the kernel. And in case of fast system calls and the syscall instruction, some model-specific registers need to be set up by the kernel beforehand as well. But overall, there is no magic here. It's rather a well-orchestrated collaboration between hardware and software in order to invoke some privileged kernel functionality from user space. All right, hope this was helpful. Peace.